So I'm here and I'm the current student here. So today I want to share our observational results of the IGM phase change SD stage of the cosmic radiation. Using one of the highest energy quasar as the background light. This is not from Akagi data. So after the recombination, the universe was mostly composed of neutral hydrogen. And it was not until the first star or the first galaxy started to shine that those infrared lights could travel around and longer being so strong absorbed by the neutral hydrogen. So we are interested in when did this radiation process start and how did those neutral hydrogen gradually become ionized, and also when does the radiation get to the end. So what we do is to observe a quasar from this stage and to see how much light is absorbed along the life side toward us by the neutral hydrogen. So this is our target, the nice hydrogen quasar to date at 3.6. And this one is the same as Dija just showed us previously in the morning. So he found this quasar at 2016 from the case 1 survey. And then later we obtained a high resolution data from the Subaru telescope. So here's Dija and Subaru telescope and Perry. So I'm using the optic wavelengths here to measure the absorption here and to see how neutral IGM along left side. So since we know that if a photon emitted from the quasar at this redshift with its wavelength less than the lambda wavelength, then it may be when it travel to lower redshift, it may be it will be redshift to longer wavelengths. For example, if it travel to here and it is redshift to the lambda wavelength, then it may be absorbed by the neutral hydrogen here. So if we compare our observational spectrum to the intrinsic spectrum, then we could know how much light is absorbed or how neutral its redshift beam. This green and blue line is the continuum line I fit using the wavelengths here. So then I measure the transmission at these redshift beams, and this is the results. And as we can see, here's a sudden drop of the transmission at redshift about 5.8, and it shows the end of the cosmic radiation. And here's the corresponding output days. So from here we can note that first when we're trying to extend the measurement to high redshift, we could see the transmission may be consistent with zero. So we may not get so much information from higher redshift. And second is that because we are measuring such low transmission, so we may not tell this fluctuation is due to the big data reduction or measure error or something else. So we try to use the second method to see the development of the radiation. So I magnify the spectrum here to see detail into it. And since we know that the radiation process is complete, so the light from the quasar may go through somewhere more neutral or somewhere more ionized along the side toward us. So the more ionized part is corresponds to the peak in the spectrum. And then so then we can measure how this neutral part or this gap constructed by two nearby peaks shrink as the redshift gets lower and lower. So here's again the results. This is a distribution of those gaps in the spectrum, and this is the gap width and the corresponding number in these redshift intervals. And here we can see again there's a sudden drop of the gap width here at about redshift 5.8. And also as the redshift gets higher, the gap width becomes larger and larger. this method and both this method and the transmission measurement are constrained by the continuum we assume. So we may not see the real situation of the development of realization. So we introduce a third method here, which is to count the dark pixel in a spectrum. And the dark pixel here we define as the pixel with its flux less than or equals 0. And here we assume that it is like the neutral hydrogen at that's corresponding redshift absorbs the light, so then there's no flux in the pixel. So then we just simply count how much dark pixel in a redshift means as a neutral fraction. Although from this method we can only provide an upper limit of the neutral fraction, but I think it is still a perspective wave because it could be extended to higher redshift. And also, the most important is that we do not need to assume any intrinsic flux. Then we could know how those relation persist. So here we again show the results, and we extend the measurement from 6.1 to 6.4, and here again we can see the development of the neutral fraction. The neutral fraction grows as the redshift gets higher, but we measure a higher neutral fraction compared to the return picture. So we may need more high redshift quasar as the sample to get statistical results. So this is a summary. We use this quasar to extend this three measurement to higher redshift to 6.5 compared to 6.1 in the past. And also in these three measurements we could see similar change of the neutral fraction. And so in the end we still need more sample to get more statistical results. So this is the end.
Okay, do you have any question? Really? Any question? Okay, that's okay. So let's move on to the next speaker. Next speaker is Narwal Tapish. He's going to talk about the most distant supercluster.